In this video, I'm going to go over the stereochemistry of alkenes, electrophilic addition reactions, and the concept of carbocations. So we see here that we have two molecules of different isomers, the trans isomer and the cis isomer. So to tell if a molecule is trans or cis is that I like to make a cut through the double bond or the alkene, and then I look at the carbons of that double bond and I determine what is my highest priority of these two carbons. So first, let's look at this first carbon over here. We see that this methyl group is a higher priority than the hydrogen. And let's look at the other carbon now. We see that this ethyl group is higher priority than that hydrogen. So we see that these two highest priority groups are opposite from each other, which means that they are trans. So now let's do the other molecule, which I like to make a cut through that double bond, look at this carbon of the double bond, and then I determine which are my highest priority groups. We see here at this first carbon, this methyl group is higher priority than that hydrogen. We see in the second carbon, that ethyl group is higher priority than that of the hydrogen. So we see that these two highest priority groups are on the same side, which means that they are cis. But this trans and cis naming system only works if the carbons of the double bond have one hydrogen attached to it. But let's say we have molecules that do not have one hydrogen attached to it, like 2-chloropent-2-ene. So we do the exact same method. I cut through the double bond like this. I determine what is my highest priority group. In this first carbon, this ethyl group is my highest priority group. In the second carbon here, chlorine has a higher atomic number than this carbon, so chlorine is a higher priority group. We see that the two highest priority groups are the same side, so this is a Z isomer. And the way I like to determine if it's a Z or E isomer is that if the highest priority groups are the same side, they are on the same side. And then let's do the other isomer. Cut through the double bond, determine which is our highest priority group. We see that this ethyl group is the higher priority group, this chlorine is the higher priority group. These two highest priority groups are across from each other, so they are the E isomer. They are E cross, or across from each other. So what if there's a tie in the first atom? So let's say we cut through that double bond here. This first atom, we know that this bromine has a higher atomic number than the carbon here, which means that this bromine has a higher priority group. But what about these carbons over here? These carbons have the same atomic number and the same groups attached to it, because let's say this is the first carbon, this is the second carbon. The first carbon is attached to one other carbon and two hydrogens. The second carbon is attached to one other carbon and also two hydrogens. So this is a complete tie. That means that we're going to move on to the next atom, which is going to be this carbon over here. So then this one carbon, the red carbon, is going to be attached to three other carbons, while the second carbon is going to be attached to one carbon, is going to be attached to three hydrogens. We do not count the previous atom that's attached to the thing we're comparing it from. We only attached it from the other groups, which we see here. The second carbon has three hydrogens. We see that the first carbon has a higher priority group, so this whole group right here has a higher priority group. We see that the two highest priority groups are on the same side of the cross that we made, which makes this a Z isomer. And let's go back to the trans and cis examples that we had. This is the old naming system. We prefer to name it through the E and Z instead. E and Z. Now let's go over the concept of carbocations. We see that we have an alkene here with an HX, where X is any halogen like bromine, chlorine, and iodine. There are two ways that this double bond can attack this partially positive hydrogen, since this bromine is partially negative. Or we could also think of it as fully dissociable H plus ions and fully dissociable Br minus ions. the double bond could either attack the hydrogen from this carbon, making this other carbon lose a bond and forming a carbocation here, or the double bond can attack the hydrogen from this carbon, making this carbon lose a bond, giving that carbon a positive charge, giving us two different intermediates here. At the top intermediate, we have a tertiary carbocation. At the second carbon, we have a secondary carbocation. And then the next steps would be that the bromine minus that got kicked off would be the nucleophile and attack the carbocation, giving us two different products. So the major product would actually be the top product, and the minor product would be the bottom product. And this is because it comes from a more stable intermediate here. And here are the stability of carbocation, the general trend of it. In the future videos, I'm going to go over more in-depth chart of this with allylic carbocations, benzylic carbocations. But for now, let's keep it simple. The more substituted the carbocation is, the more stable it is. The less substituted it is, the less stable it is, the less substituted the carbocation is. We see here the tertiary carbocation is the most substituted with 3 carbon groups attached to the carbon with the carbocation. The secondary carbocation is the more substituted carbocation with 2 carbon groups attached to the carbon with the positive charge. The primary carbocation is the least substituted carbocation because we see that this carbon holding the positive charge only has 1 other carbon attached to it, and then the very least stable, very unstable carbon has no carbon groups attached to it. And these are based on the inductive effect and the hyperconjugation effect. So what the inductive effect is that the R groups inductively donate electrons to the carbocation through the sigma bond directly in between them. The hyperconjugation effect is that the sigma bonds between the R groups and the hydrogens or other R groups will directly donate to the empty p orbital of the carbocation. So the more R groups there are that are attached to the carbocation, the more stable it is because the more electrons are being donated to the positive charge. That means they are destabilizing or decreasing the net charge of the molecule, which makes the molecule more stable. Now let's go over the stereochemistry of these. Markovnikov's rule is when the bromine is attached to the more stable carbocation. We see that in this molecule, this carbon would form the most stable carbocation, which means that this is the Markovnikov's rule. Anti-Markovnikov's rule is when the nucleophile would attach to the less substituted carbocation. We see here this carbon would be the less substituted carbocation, which will attach here, making this the anti-Markovnikov rule. And for this specific type of reaction, HX with a peroxide like H2O2 or ROOR, this only works with HBr. This would not work with HCl or HI. If we see HCl or HI on top and peroxide on the bottom, we would get the Markovnikov rule instead of the anti-Markovnikov rule. Now let's do some practice problems over here. We see that we have an alkene with HBr. We know that this carbon here would form the more stable carbocation, which means that we have to use the other carbon of the alkene to attack the hydrogen, kick out the bromine. This will be attached to the hydrogen. That carbon lost the bond, so that carbon now has a positive charge. The bromine got kicked out with a negative charge, so that negative charge is going to attack that positive charge. And then we get our final products here. So now let's go over a tricky problem here. We see that this carbocation is going to be more stable than the other carbocation, which means that the other side of the alkene is going to attack that hydrogen, kick out the bromine. And this carbon here lost the bond, so this carbon will have a positive charge, but the Br minus would not attack that carbocation right away, because whenever you form a carbocation intermediate like this here, you always look out for any rearrangements that you could do to become more stable. So we see here, this is a secondary carbocation. We have to look to the right and left of that carbocation to see where it could go to become more stable. Let's look at the right side of it. If it moves there or shifts there, that will become a primary carbocation, which we do not want. But let's look at the left side now. If the carbocation moves here, that forms a tertiary carbocation, which is what we do want. So we could do a hydride shift here, where that invisible hydrogen can move to that carbocation and form a carbocation in the tertiary position right there. And this hydrogen is now here, but I'm going to keep that as invisible. Now the bromine minus ion can come in and attack that carbocation, giving us our major product. And then this right here is specifically called a hydride shift, where we moved the hydrogen to that carbocation. But there's another thing called a methyl shift, where we do the exact same thing. We see here this carbon would form the more stable carbocation. We attack the hydrogen from the other side of the alkene. That would give us this carbocation intermediate. We look for our more stable carbocation intermediate, which we see it can be on the left side, but in this case we're going to do a methyl shift instead of a hydride shift because we do not have any hydrogens here. So then we would have this over here, where this methyl group here is now over here, and then the Br minus group will now come in and attack that carbocation and give us our major product. So this right here is called a methyl shift. Okay, and now I'm going to go over the general aspects and general trend of these electrophilic addition reactions. We see that we have an alkene here and an electrophile with a nucleophile, where we break the double bond and break the bond between the electrophile and nucleophile and form the bond between the carbons of the alkene and the nucleophile and electrophile. So the bonds that are broken are the bonds of the alkene and the bond of the between the electrophile and nucleophile. The bonds that are made are the bonds between the carbons of the alkene and the electrophile and nucleophile. Now let's go over the stereochemistry of these reactions. These stereochemistry could be syn addition or anti-addition. What syn addition is that the electrophile and nucleophile attach on the same side of the alkene. Anti-addition is when the electrophile and nucleophile attach on the opposite side of the alkene. So here's a mechanism of it. We see that this carbon here of the alkene attaches to that electrophile, kicking out the nucleophile. We see that this attack can attach this electrophile on the top or bottom side. Let's say it attaches on the top side, and then this is the sp2 carbocation over here. This nucleophile can do an SN1 reaction where it can attack on the top side or bottom side. If it attaches on the top side, then that would be syn addition, where they both attach on the same side. But if it attaches on the bottom side, then there would be anti-addition, where they are opposite from each other. Now let's go over the regional selectivity of these reactions. They could either be Markovnikov or anti-Markovnikov, which I went over previously. If they are Markovnikov, then the nucleophile will attach to the more stable carbocation. If they are anti-Markovnikov, then the nucleophile is going to attach to the less substituted carbocation intermediate right here. And here's the mechanism for the Markovnikov rule. The mechanism for the anti-Markovnikov product depends on the reaction, like hydroboration oxidation or the radical hydrohalogenation. So now let's go over some practice problems of this. We see here this carbon will give us the more stable carbocation intermediate. So we are going to use the other side of the alkene to attack that hydrogen. Form the carbocation there. We form a carbocation intermediate. We see if we can form a more stable carbocation intermediate, which in this case we do not have any places, because this would give us a secondary carbocation. This would also give us a secondary carbocation, and the other one would give us a tertiary carbocation, which is the same. So we do not have to do any shifts here. So then we bring in our nucleophile Br minus to attack that carbocation and give us our final product. Now let's move on to the next problem here. We see that we have an acid with a neutral molecule. So the acid here will look for a base, and this base here in this case would be the alkene. We see that this carbon would form the more stable carbocation, so the other carbon is going to grab that hydrogen, and the middle carbon will lose a bond, where I'm going to show that this is an invisible hydrogen now. Now the water molecule, where the oxygen has lone pairs of electrons, will attack that carbocation. And now the very final step here is to deprotonate this water molecule to neutralize it. Okay, now let's move on to the next one. We see we have Br2 and a non-nucleophilic solvent, which means that we are going to attack one of the bromines and then kick out the other bromine, and then as this bromine is getting more electrons and this alkene is losing electrons, this is becoming more electrophilic, this is becoming more nucleophilic, where this bromine will attack the other side of the alkene and form this bromonium ion over here. And then this bromonium ion makes these carbons very electrophilic. We're going to choose one of them to attack, kick out the other bromine. And this would happen in anti-addition, where, because we see here, this attack is SN2 like, where there's a backside attack. So the bromines here would be anti to each other. Br. But in this case, we have a plane of symmetry, so we do not have to include stereochemistry in this case. But if there was chiral centers, then I would include enantiomers of the anti-product. And this is if we have non-nucleophilic solvents, but let's say we have nucleophilic solvents like water and alcohol. So we do the exact same thing. But this time, we have a competition between Br minus and water. You might think that Br minus is a stronger nucleophile than water is, and in general it is, but in this case, think of the solvent as being in excess, and we have way more water molecules than we do have bromine molecules, so the volume of the water molecules will overpower the bromine molecules, which makes this water molecule the nucleophile. So this water molecule will attack, kick out that bromonium ion. So this oxygen here of the water molecule attacked that carbon, so that carbon and oxygen is now attached. Now the very last step is to deprotonate that positive charged oxygen to make it neutral, and that will give us our final products here. Now let's go over the alcohol situation, which is very similar to the water situation, but just different nucleophilic solvents. So we have a competition between the Br minus and alcohol, but alcohol overpowers it because there are excess, way more alcohol molecules than Br minus. We know that this alcohol oxygen here attached to this carbon, so we draw the new bond between that carbon and that oxygen. That oxygen is attached to one hydrogen, one R group, and since it has 3 bonds, it has a positive charge. And then the very last step is to deprotonate this positive charge oxygen with the Br minus that we formed, and this would give us our final product over here with the OR group of the alcohol.